Okay. In the previous discussion, we have discussed about importance of calculus. That include differentiation and integration. Now, today we will discuss something about the importance of differentiation, its application in finding maximum and minimum value of a function that we call local minima, local maxima, the absolute maximum of a function and absolute minima of a function. I want to show in detail how we proceed to find out. So, in order to show it, I just want to take two functions, a function that is sine function and its derivative cos function. Okay. Now, I take the function sine function as the original function, sine x. Okay. Now, the graph of sine x is drawn like this. It's very big. It's drawn like this. Like this. Okay. And its derivative is cos x. Okay. Is cos x. And cos x is represented, okay, like fix the points first. Here, this point corresponds to x is equal to pi by 2. This is x axis. This is y axis. Same thing, this is y, this is x. Okay. This point corresponds to pi by 2. This point corresponds to pi. This lowest point corresponds to 3 pi by 2, and this point corresponds to 2 pi. Okay. So I take this point, but this line almost on this same straight line is y-axis. Okay, so I take this line from here, and I can take this line from here, and I can take this line to take corresponding points. Okay. So this point corresponds to pi by 2. This point corresponds to pi. Okay, let's try it afterwards. This highest value of sine x is 1, lowest value is 0. This is 1, cos is 0. Okay. Now, cos function goes like this. Okay. So this angle corresponds to pi by 2. This angle corresponds to pi. This angle corresponds to 3 pi by 2. This angle corresponds to 2 pi. Okay. So the original function is sine x. So differentiation of sine x yields cos x. Okay, that is cos x is the general expression of the graph that represents the value of the slope at different points of the original function sine x. Okay, of different points of the graph of the original function sine x. Okay. Now we know that from this graph is already drawn, and from this graph we know that this highest point correspond the slope of the tangent of this highest point is 0, because this tangent is parallel to the horizontal line or the x-axis. So the slope of this tangent, this is the tangent. Okay, the slope is 0. Same thing. This is the lowest point, and when I draw a tangent here, the slope is 0. Slope is 0. But cos x is a general expression of the slopes of the function sine, slopes of the graphs of the function sine x, slopes of the function sine x, graph of the function sine x. So if I set d sine x by dx is equal to 0, this will imply cos x is equal to 0. Is equal to 0. Okay. Therefore, if cos x is equal to 0, then x corresponds to x is equal to pi by 2 or 3 pi by 2. Okay. I'm going to show how shall we proceed to find the maximum value and minimum value of a function, by calculation, by using the differentiation, without even drawing the graph, That's what I'm going to show, But to show that, I am just drawing this graph for visualization, If x is equal to pi by 2, and when I said the general expression of the slope of the original function equal to 0, we get x equal to pi by 2 and or 3 pi by 2. These are called critical points. Critical points. Critical points. X is equal to pi by 2 or 3 pi by 2. Critical points. Now at critical points, we know that x and the graph has a lowest value or the function has a lowest value or a highest value. Till now we don't know which one is the highest or which one is the lowest. To find it out, I proceed further. I find the second order derivative of the function, that is represented by f double prime x. That is, we know that derivative of a function f is represented as df by dx, is equal to f prime x by fx is equal to f dot x by, like this. Even though they have different names, they have different even though they have different modes of representation, they have the same meaning. Now f is at 2 primes, 2 here in the upper, in the subscript, in the superscript, I write two oblique small lines, dashes, and this represents second order derivative. Now, second order derivative of x at x is equal to pi by 2, is equal to limit delta x tends to 0, f prime pi by 2 plus delta x minus f prime pi by 2 divided by delta x. But we have already known that the first order derivative of the function at pi by 2 is equal to 0. That is, slope is equal to 0. Therefore, we can write it as like this: limit delta x tends to 0, f prime pi by 2 plus delta x divided by delta x. Now, let's see. If delta x is equal to a negative value, then pi by 2 plus a negative value is equal to a value lower than pi by 2. That means this angle will be less than pi by 2. If this angle is less than pi by 2, this first order derivative will represent the slope of the function, slope of the curve lying to the left of the vertical line touching the angle pi by 2. And so, all the slopes of the points corresponding to this curve will be positive because they make positive angles. They make angles less than 90 degree and positive angle less than 90 degree. Okay, they have positive angles less than 90 degree. Therefore, they have positive slopes. Therefore, the upper value will be positive. But I have taken the delta x to be negative. Therefore, when I divide positive value by a negative value, it yields negative value. Negative value. Negative value. So, okay. Again, let us take delta x to be positive. Okay. When I take delta x to be positive, this argument will be greater than pi by 2 because some positive number is added to the angle pi by 2. Therefore, this angle will be greater than pi by 2. Okay. Therefore, this part of the derivative of the function will represent the slope of the curve lying to the right of the vertical line touching the angle pi by 2. Okay. Therefore, this slopes will be like this, and as they make negative angles with the positive x-axis, it will give negative slope. Therefore, if delta x is positive, it will give the upper value of this fraction will give negative slope, therefore negative value. And if I divide negative value divided by positive value, it yields negative value. That is, in both the cases, whether either I take delta x to be positive or delta x to be negative, that means in either cases it yields negative value. That means if the point that corresponds to the highest point of the curve, okay, then the second order derivative of the function, okay, at the critical point yields negative value. Okay. This is the first case. Again, if I take the lowest value here, okay, this I set tangent set to be 0. Okay, if I take the second order derivative around the point 3 pi by 2, okay, second order derivative at x is equal to 3 pi by 2. Okay, then this is equal to limit f prime, okay, 3 pi by 2 plus delta x divided by minus f prime 3 pi by 2 divided by delta x. Okay. Here f prime 3 pi by 2 is equal to 0. That is, at this critical point, the slope of the function is equal to 0. Okay, that is already known. Therefore, this remaining part becomes delta x tends to 0. Limit delta x tends to 0. Okay, f prime 3 pi by 2 plus delta x divided by delta x. Okay, delta x. Okay. Here, if delta x is taken to be negative, okay, then let's see here. If delta x is taken to be negative, then a negative number added to 3 pi by 2 yields angle less than 3 pi by 2. Therefore, the slope will represent the part of the derivative of the function will represent the slope of the curve lying to the left of the vertical line touching the point 3 pi by 2. That is this region. Okay. Okay, this region. In this region, the graph is decreasing. So, if I take the slope of a point here as that tangent makes negative angle with the positive x-axis, the slope value will be negative. Okay, if delta x is to be positive, negative value, okay, that means the numerator of this fraction will be negative, and as the denominator is taken to be negative, a negative number divided by a negative number is positive. Is positive. Okay. Is positive. Okay. So, okay. Again, if delta x is taken to be positive value, as a positive value added to a 3 pi by 2 will be larger than 3 pi by 2. Therefore, the slope of the graph represented by this function or this value will correspond to the slope of the points lying to the right of the vertical line touching the point 3 pi by 2. That is, points lying in this region. That is, in this region, the graph is increasing. Therefore, the slopes will be positive as the tangents make positive angles with the positive x-axis. Therefore, positive acute angles with the positive x-axis. Therefore, the slopes will be positive. Positive. Okay. And I have already taken delta x will be positive here. Therefore, a positive number divided by positive is positive. Therefore, it yields positive value. Okay. In which case, at the lowest value of the function. Okay. That means after finding the critical point by setting the first order derivative of the given function to 0, if the value of the second order derivative at that critical point is negative, then that critical point corresponds to the highest value of the function. That means it gives the local maxima. This will yield local maxima. Local maxima. Again, after finding the critical value of the function by setting the first order derivative of the function equal to 0, if the value of the second order derivative at the critical point is found to be positive, then that point corresponds to the value of the function that gives the lowest value of the function as compared to the nearby region, that will yield local minima. Local minima. Local minima. Hence, it is concluded that to find the local minima or local maxima, okay, without even drawing a graph of the function, okay, I set the first order derivative equal to 0. That is the slope equal to 0, and then find out the critical points. Here, critical points, these points, critical points, and then I find the second order derivative of the function. That means the derivative of the slope again. And I find the value of the derivative, second order derivative at the first critical point. Okay. If that value yields negative value, then that corresponds to the local maxima, okay, of the function. And if the value of the second order derivative at the critical point yields positive value, then that point corresponds to the local minima of the function. Okay, this is regarding local maxima and local minima of the function. How to find the local maxima and local minima of the function using the differentiation process. Okay, without even drawing the graph. Okay, yes, already that's okay. Now, next, I just want to find out the absolute maxima and absolute minima of the function in a closed interval. In a closed interval. In a closed interval. Okay. For that purpose, same thing. I just set the critical points. I just find out the first of the derivative, then set the first of the derivative equal to 0. Set the first of the derivative equal to 0 and find out the critical points. Okay. And then I compare. I find out the value of the function at the endpoints. Value of the function at the endpoints and at the critical points and compare them. And from that comparison, there one value will be the highest and one value will be the lowest. And that highest value will correspond to the absolute maxima of the function at the closed intervals. And the lowest value corresponds to the value of the function at that. The lowest value will be the absolute minima of the function at that closed interval. Within that closed interval. Okay. In finding the absolute maxima and the absolute minima of the function, we don't even use the second order derivative of the function. We just need the first order derivative to find out the absolute maxima and absolute minima of the function. But in order to find the local minima and the local maxima of the function, we use the first order derivative and the second order derivative of the function. Okay. This is all about. I just want to discuss regarding the application of differentiation in finding the maximum value and minimum value of a function.